Next time you're at the gym, take a close look at the equipment smoothly spinning away in the cardio section. Beneath those plastic casings is a precise orchestration of metal linkages and pivot points. We are going to strip away the casing and rebuild one of these machines from scratch. Using just a side profile photograph and dynamic geometry software, we'll recreate the exact mechanical skeleton driving that motion. This is our target, a fully interactive digital twin where every geometric point and line maps perfectly to the physical parts of the machine. By constructing this model step by step, we'll see exactly how these overlapping rigid bars force a seemingly simple fluid motion, and will prove that the so-called elliptical stride is actually a carefully engineered illusion. Step 1 is setting up our digital canvas. We start by importing a clean, side-profile photo of the machine directly into the background of our geometry workspace. Before doing anything else, you must lock this image to the background grid. If the photo shifts while we are plotting coordinates, the entire geometric framework will fall apart. Now we build the engine. Take a look at this solid blue point labeled C on your screen. This is the main axle of the machine's lower drive wheel, and it acts as the stationary anchor for our entire model. From that central axle, draw a circle outward to match the outer edge of the wheel hub. This blue circle represents the exact path that the physical crank arm travels. Next, place a point directly onto the edge of that blue circle. This is point P, our moving drive point, representing the joint where the metal arm connects to the rotating wheel. Every linkage system, no matter how complicated the final output looks, relies on a single rotating anchor point like this to power the entire mechanism. With our engine built, we face our primary engineering challenge. How do we mathematically connect the lower drive arm to the upper handlebar, ensuring neither bar changes its physical length as they rotate? We solve this by translating solid materials into mathematical rules. A metal arm has a fixed length. In geometry, all points at a fixed distance from a center form the radius of a circle. Let's look at the large dashed blue circle labeled D. By drawing this circle outward from our moving drive point, we've mapped every possible location the end of that lower connecting bar could reach. We repeat the process for the upper handle. Find the stationary pivot point near the console, point E, and draw a dotted green circle radiating outward. This circle defines the full reach of the upper handle's lower segment. Where those two auxiliary circles cross, right here at point G, is the only mathematical location where both rigid metal arms can meet without breaking. This is the machine's moving knee joint. Connect those pivot points with solid line segments, representing the green handle and the orange drive bar, and the complete structural skeleton is locked into place. The software is now enforcing the same physical constraints as the forged steel in the gym, turning rigid lengths into intersecting geometric rules. To see how this skeleton moves, look at the orange lower bar. We place a final point exactly where the user stands, labeled here as the foot. Pay close attention when placing this point. You must ensure the foot point is strictly locked to the dynamic bar segment itself. If you accidentally pin it to the static background photo, your model will freeze up. With the foot point properly attached to the bar, right-click it and activate the software's Show Trace feature. This will record the exact path the point travels through the air. Now grab the main drive point down at the wheel and spin it a full 360 degrees. As the skeleton flexes, the foot point actively draws a continuous red loop behind it. Because the foot point is bound to the lower bar, sliding it slightly forward or backward along that segment will actively alter the dimensions of the trace, shortening or lengthening the stride. This dynamic tracing is exactly how biomechanical engineers test and tweak the ergonomics of a walking path long before a single piece of metal is cut on the factory floor. Let's analyze the shaded red loop directly beneath the foot point. Notice the asymmetry. The curve tapers on one end and widens on the other. Mathematically, it's a teardrop shape. Despite the machine's name, it does not produce a true geometric ellipse. Once you understand how these linkages operate, fitness equipment reveals its internal logic. Every handle and pedal operates through a specific set of geometric intersections. You could apply these exact same principles to capture and trace the intricate cable paths and pivot joints of early mechanical rowing equipment. Or bring in a photo of a classic stair climber and model how its alternating arms transfer weight smoothly from one pedal to the other. The physical world is built on these principles of movement. Tracing these lines shows the math that governs the machines we use every day.